Hey friends, welcome to the next lesson in probability unit. This one's going to be called independent and dependent events. So what we're going to do is we're going to talk about what these two words here mean. Before we get going, maybe I want you to think about what that means in your real life again. Independent means you're on your own, right? You're working, you're not at home, no one's paying your bills, you take care of yourself. You don't depend on anybody. Dependent event means I'm counting on someone to take care of me. I'm a dependent. I'm living at home, someone's helping me pay my bills, maybe buy my groceries. Same sort of idea in this little section. Let's check it out. So imagine you have a fair coin, a jack, a queen, and a king of hearts from a deck of cards. Create a sample space for the experiment of flipping a coin and drawing one of the cards. Okay, so if I'm thinking of the coin, I could have heads or tails. Or if I'm thinking of my cards, I could have a jack, a queen, or a king. So what does my sample space look like then? Well, I just need to put these things together. I could have a head and a jack, a head and a queen, a head and a king, or I could have tails and a jack, tails and a queen, tails and a king. So there's my sample space right there. Now, can I use the fundamental counting principle to prove that this is true? Absolutely. This is 2 times 3, which is, there's 6 events right there. So this fundamental counting principle is always a nice handy way for us to figure out how many outcomes in a set, how many ways can I do something. Let's continue on. So now we know there's 6 outcomes. Easy. Now let's define it a little bit more. Let A be the event of getting tails on the coin. Let B be the event of drawing a queen. So what is the event of getting tails on a coin? Well, that's 1 over 2. What's the probability of getting a queen from the cards? 1 over 3. C says probability of A and B. So let's figure out what that means first. That's the probability of getting a tails and a queen. Well, I can go back up and just count. How many ways did that happen in my sample space? Well, there was only one way out of 6 ways for me to get a tails and a queen. Now, it says number 2, is there a relationship between 1C and 1A and 1B? Yes. Do you notice that if I go 1/2 times 1/3, I end up with my answer for C? Interesting. Okay. 3. Does event A have an effect on event B? Does what happened on the coin affect what happens on the card? No. They are independent of each other. It has no effect. Drawing a card and flipping a coin have no effect on each other. Alrighty. Important question right there. Let's keep going. Part 2. Imagine now I give you the entire deck of cards. And I say draw one deck of cards, draw one card from the deck of cards. Determine the probability of the card as a king. Cannot speak. Okay, probability it's a king. Well, I remember that there's 82 cards in a deck, and there's 4 kings. Hey, I could do this as well, 1 out of 13. Set the card aside, draw another card. What is the probability the card is a 7? Okay, well, if I set this card aside, what's happening here is I'm asking for a 7 given already have a king. Given that I've already got a king. Well, how many 7s are there in the deck? There's 4, But how many cards are left now? 51, not 52, because I set the card aside. Does the first event affect the second event? The probability? Absolutely, absolutely, because it lowered how many possible outcomes there were. So this would be known as dependent. It has an effect on what's happening next. Those are our big terms for the day. So in the past, we would ask, does order matter? Does order not matter? Permutation, combination. Well, what I need to introduce to you today is, do we affect each other? So if I do not affect, those are known as independent. And the nice thing is, I can simply just multiply these two events together. If they're dependent event, meaning it does have an effect on each other, I can still multiply these together, but here's where it looks a little different. So it's the probability of the first event times the probability of the second event, but this here is the probability of the second event, B, given such that A has already happened. So this is my second event right here, and what this says is B given that A has happened. Now, most of the time we might not even need to use that formula, but on the odd occasion, when the question gets a little wordy and complicated, it'll be handy to maybe write that down. These are both on my formula sheet. So independent, dependent events, it's this and this, so we multiply. We just need to ask ourselves now, do we need to do something? Does the first event have an effect on the second event? Okay, I want you to hit pause. After you try, read example 1, hit pause, answer the questions, and see if you can tell me if these things are independent or dependent. And when you're done, resume the video. I'll see you soon. Okay, you're back. You tried to fill in the table. Let's see how you did. See if our answers are match. So first one, I'm picking a 5 from a bag with sheets with 0 to 9. The key word I see there is I'm replacing it. So I'm picking a 5 and picking a 6. Well, these are independent because if I put the slip back in, I still have the same number of slips when I pull the second number. 3 students are chosen for an executive council. Dean is chosen as vice president, Sally's president, Harvey's treasurer. Well, this is absolutely dependent because as soon as Sally is president, she can't now have a second role. So that's going to affect how many people are left to then be vice president, treasurer, so on and so forth. Okay, so however you want to word that, there's some specific roles in there. Specific role of president, and I can't have 2 positions. No can have 2 positions. So it's going to decrease the number of chances or people that could be available for the next one. Okay, drawing straws. Well, I don't even need to read the rest of it. Drawing straws is always dependent. Because if I draw the one straw that I don't want right off the bat, everyone else is free. But if I don't draw that straw, then the probability just got worse for the people behind me. So it definitely has an effect on who's coming after. Selecting a red marble from one bag and a green marble from a second. Well, they've got nothing to do with each other. They're in different bags, independent, different bags. No effect on each other. Okay, this last one here I really like, because this is probably the only time, no pun intended, probably, that we actually need to use our formula. So what this says is it goes, whatever event A is, the probability it happens is 0.3. Whatever event B is, the probability it happens is 0.7. And P, A, and B is 0.25. Okay, Well, to figure out what this is, I'm going to go and I'm going to use my formula. I'm going to say, what's PA times PB? Well, that would be 0.3 times 0.7, which is 0.21. But it says up here that it should be equal to 0.25, which it does not. So what this means is these are dependent events. This here is known as my test for independence. And we failed it. So if PA times PB does not equal PA and B, guess what? I'm dependent. Okay, that's a really good one. I want you to take a look at that again. Maybe something that I see on a quiz or a test. Hint, hint, nudge, nudge, wink, wink. All right, almost done this short little lesson. If a regular six-sided die is rolled 3 times, what is the probability? Okay, so now we're going to start mixing up dependence and independence of turning up a 5 all 3 times. So can rolling a 5 have an effect on rolling the 5 on the next roll and the next roll? No. So the first thing I'm going to say to myself is this is an independent event. There's no effect. So I want the probability of a 5 and a 5 and a 5. And I always want you writing these probability statements out. Well, since it's independent, this is P5, probability of getting a 5, times the probability of getting a 5, times the probability of getting a 5. Well, the probability of getting a 5 any one time is 1 over 6. So that's 1 over 216. Easy peasy, lemon squeezy. B, a card is drawn from a deck and a second card is drawn in capital letters without replacement. I wish they wrote it like that on my diploma. Not a chance. So we need to be looking out for those words. Well, without replacement now means right away that this is a dependent event. What happens on the first is going to affect what happens on the second. So what is the probability of drawing a 5 and then a red queen? So I want P5 and maybe I'll write it like this, red 5, and I want a black queen. Well, what this is going to give me then is the probability of the first event, which is me getting a red 5, and the probability that I get a queen that's black, given that I've already had a red 5. So that's the proper way to write that down, just like that. So did I really need to write that down? In 30-2, the answer is probably no, but I am always going to request that you do it. What's the probability I get a red 5? Well, there's 2 of them out of 82. What's the probability that I get a black queen? Well, there's 2 black queens, but now I need to remember this is a dependent event right here. I've already pulled a 5, so there's only 51 cards left for me to select from. So put that in my calculator, and I'm going to get 1 over 663. That's a really small probability. Again, always leave things in fractions unless you have been given rounding instructions. Okay, last one. Brenda has a 75% chance of sinking a foul shot. If she takes 5 shots, what is the probability she sinks at least 1? Okay, first question. Is this independent or dependent? Well, it says she's got 75% chance of sinking any shot, and really, what happens on the first doesn't happen on the second. So this is independent. So the probability she sinks at least one. Well, that means I get 1 in, or I get 2 in, or I get 3 in, or I get 4 in, or I get 5 in. Oh, what a pain in the butt. When I start getting that many cases, I want to start thinking, is there a better way to do this? Absolutely. At least one. Do you remember the shortcut here? The complement. Meaning what I don't want. So the probability of at least one is equal to all possibilities, all total, minus what I don't want. Well, what I don't want is 0 in, right? She gets none in. Well, all total, that's 100%, which I'm just going to write as 1, minus she gets none in. Well, that means on her 5 shots, she gets none in. Well, if there's a 75% chance she gets it in, that's 3 out of 4 there that she scores. What's the probability that she doesn't score? Well, 1 out of 4. But she doesn't get it in on all 5 shots. So 1 out of 4, 1 out of 4, 1 out of 4, 1 out of 4, 1 out of 4. Or let's write this in a better way. 1 minus 1 over 4 to the exponent 5. There we go. And what we're going to get here is going to be some really small number. That's 1 minus 1 over 1024. And that should be, let me just clear that out. I'm running a little bit out of room there, friends, so I'm just going to erase that. Well, 1 minus that is 1023 over 1024. Now, if you put that in your calculator and turn that into a decimal, that's going to be like 99%. If I'm a gambling man, I'm gambling that Brenda here is going to hit probably 1 of her 5 shots. She's pretty good at it. So when I start seeing these words, at least, at most, I want you thinking complement. Maybe there's a better way to do the question. Okay, that is it, my friends. So as you're starting your practice here, the first question I want you asking yourself is, does order matter? And then, does the first event affect the second event? We need to be able to combine these things together. Is it a permutation or a combination, or am I talking about an independent dependent question? Okay, good luck to you. I will see you soon.